Hello viewers, Pop's Team Talk Show is back with the third and final episode of our mini-series, The Forgotten Twin. As you know, in this series, we have requested selected physicists to revisit Bose's second paper on quantum statistics, which he wrote immediately after finishing his first paper, which is today a celebrated paper, Planck's radiation law and light quantum hypothesis. Now, in the previous two episodes, Professor Partha Ghose and Professor Ananda Dasgupta, they have shared their views on Bose's second paper, which is not talked about at all, unfortunately. In this episode, we have got Professor Sreerup Raychaudhuri to speak to you. Professor Sreerup Raychaudhuri is a theoretical physicist with expertise in electroweak interactions and collider physics. In his own words, my work is a meeting place between theoretical ideas, experimental data, and numerical computation. I also retain a lifelong interest in pedagogy and the history of science. He started his teaching career at IIT Kanpur, and after a few years, he moved to Tata Institute of Fundamental Research in Mumbai. There he spent 17 long years as a professor in the theoretical physics department, and now Professor Raychaudhuri is attached to the Benares Hindu University as a professor of physics. Over to Professor Raychaudhuri.
It is well known that Satyendranath Bose wrote a famous paper from Dhaka University and sent it to Einstein, who recognized its novel and far-reaching consequences and had it published in the Zeitschrift für Physik, of which he was the editor. What is not so well known is that a few months later, Bose wrote a second paper, rounding off his earlier work and proving the validity of what we now call quantum statistics. This paper, which was as brilliant as the first, requires to be rehabilitated, if for no other reason than to show that Bose's first paper was not a flash in the pan. In fact, it is the answer to all those who think that Bose arrived at his result by accident and everything after that was done by Einstein. The paper shows how deeply and clearly Bose had thought about the problem and why his vision was clearer than that of the top physicists of the time, including the great Einstein himself. And so we will discuss this paper of Bose, which I flash at you in its English translation. Remember, Bose wrote his manuscript in English, and Einstein translated German for publication. Bose's original is, however, lost, and this is a later translation back into English. As you can see, it is titled Thermal Equilibrium in the Radiation Field in the Presence of Matter. And Bose's address is curiously given as Romna and not Dhaka as you would expect. The mystery is solved by noting that the area of Dhaka where the university stood and still stands is called Romna. Maybe it was Einstein himself who was confused between the two. However, to understand the full significance of what Bose did, we need to go back and see the antecedents of this work, to see what the problem was, how others had tackled it before him, and what innovations were made by Bose. So we start from a very interesting result proved in 1859 by Gustav Kirchhoff. He showed that if radiation is confined inside a closed container, a Hohlraum in German, and comes to thermal equilibrium by repeated reflections from the inside of the container, then it will attain the same spectrum as a perfect black body. And to arrive at this theorem, he used only thermodynamic arguments, and hence this is valid whatever the nature of the radiation may be. Of course, in those days, Maxwell's theory had just come, so people thought of radiation as electromagnetic waves in the infrared for thermal radiation. Such waves would then form a standing wave pattern inside the container, as I show you in this little cartoon. Now, if you make a small hole in the side of the container, the radiation will shoot out, and naturally it will be of the black body type. An equally important theorem was proved by Hermann Weyl in 1912. He proved, using purely mathematical arguments, that the radiation inside the cavity assumes the black body spectrum irrespective of the shape of the container. This means that if we replace a spherical cavity by a cubical one, under equilibrium conditions, we will have exactly the same black body spectrum. And once again, if you make a little hole in the side of the container, black body radiation will stream. So these two theorems, one by Kirchhoff and one by Weyl, made it very easy for other scientists to study black body radiation by studying cavity radiation. Now it is well known that the correct form of the black body spectrum was discovered by Max Planck in 1900, and in deriving this formula, he had to assume that the radiation was emitted from the walls of the container in packets or quanta of energy. That is a pulsed emission and not a continuous outflow. So imagine a cavity as before, where the walls emit a pulse of radiation, or rather a series of such pulses, which can be thought of as short wave trains. These, according to Planck, then merge into a continuous pattern of standing waves. So in a famous analogy, Planck likened this process to the emergence of drops of water from a tap, which then merge into a continuous stream. Sadly, Planck's idea did not last more than 5 years. In 1905, Einstein published his theory of the photoelectric effect. Now, in this theory, he showed that radiation is absorbed as quanta, which are the same as Planck's quanta. That is, a material absorbs a specific quantum or wave train, and this energy goes into pushing out an electron. So imagine a photoelectric material, then a wave train comes in, or a quantum of energy. It's absorbed and photoelectrons come out. So the point here is that if the radiation is emitted as quanta and then merges into a continuous wave, then it must again disintegrate into quanta just before the photoelectric material. Just before it hits the photoelectric. At this point, it must disintegrate into quanta. And how will it know beforehand that it is going to hit the material block? That would violate causality. The only explanation is that the radiation remains as quanta throughout. But then, what happens to Maxwell's equations and the beautiful theory of classical electrodynamics? So this strange behavior, the radiation is somehow not following the rules, was deeply upsetting to the great minds of the day. Now, they included De Bayer, Nathanson, Camerlingons, Ehrenfest, Einstein himself, and the young Pauli. And they all tried their best to understand why radiation was behaving in this unexpected way. But ingenious as their derivations were, none of them could rid themselves of Planck's original idea that it was the container was somehow responsible for breaking the continuous radiation into discrete quanta. It was the container which was the culprit. They could not imagine that quanta could be a natural state of radiation. It is Satyendranath Bose who was able to achieve this leap of imagination. Sitting in faraway Dhaka, he was able to drop the role of the container altogether. Now, there are some who say that he could do this only because he was working in isolation, but nothing could be further from the truth. He was familiar with all the papers of these European scientists and all their ingenious ideas of why the container is the culprit. This included Einstein's theory of spontaneous and stimulated emission and absorption and matter-radiation interaction. All these papers were with him and he had read and studied them. But what Bose did was to assume that the quanta, that is the photons, constitute the natural state of radiation, and therefore radiation confined inside a cavity was just the same as gas molecules confined in a similar cavity. In the cartoon, the blue dots are these photons, and we see the continuous role is limited to holding them inside a confined space, with the additional fact that it can randomly absorb quanta and re-emit quanta. But it does nothing to create wave trains out of continuous waves, as the others had been assuming. Bose then applied statistical counting techniques to these photons, just as Boltzmann and Maxwell before him had applied to gas molecules. The net result, the Planck distribution formula. Now, in arriving at this result, Bose required to use three ideas which were novel at the time, and all of which were precursors of quantum mechanics, which came soon after. These included phase cells of volume h cubed, which is nothing but the uncertainty principle of Heisenberg, which came later. Then he treated the photons as indistinguishable. Now, this becomes meaningful only with the wave-particle duality argument of de Broglie. And finally, he guessed that the photon has a spin, either clockwise or anti-clockwise. All of these were proved correct later when quantum mechanics came. As is well known, Einstein, when publishing Bose's paper, was enthusiastic about the first two ideas, but refused to believe the third because he found it unthinkable that a point particle could carry angular momentum. When publishing the paper, he replaced spin by polarization on his own, something which is meaningless for a particle. He then complained to Bose that his derivation was not rigorous because of this polarization business. Despite all these hiccups, however, it was, after all, Einstein who gave Bose his break, which the British journals had not done. He had sent them to the British journals first, but they simply rejected his work. In fact, enthused by Bose's ideas, Einstein worked hard to extend them. In fact, it was the first time in his life that he was extending ideas due to someone else. In all his previous work, he had been the pioneer, and others had extended his work. And so, Einstein applied Bose's technique to a gas of massive particles and arrived at the formula which is now known as the Bose-Einstein state. He then drew the conclusion that at very low temperatures, such a gas will pass into a different phase, which we today call long-range correlations. But this phase is now called a Bose-Einstein condensate. Going further, Einstein applied Bose's counting method to lattice excitation, phonons, and was able to derive the well-known Dulong-Pettit law and even find temperature-dependent corrections. Now, we may note that all these were single-author papers by Einstein, even though he clearly and fully acknowledged that the method was discovered by Bose, but the authorship of these papers was solely his. Now, during this period, Bose was very much there in Europe. He was working in Madame Curie's lab at Paris, and Einstein could have easily called him to Berlin to collaborate. But he didn't. He called Bose only after he had made all these discoveries on his own. At Berlin, Einstein asked Bose to work on matter radiation interactions. This is the subject which he had avoided in his own work. Now, this was Einstein's pet project, spontaneous emission, spontaneous absorption, and so on. It was something which Bose had never shown much interest in. And in fact, Einstein had already cleared out the easy problems and only the hardest ones were left for Bose. Not surprisingly, he made zero progress during the time he was in Germany. Now, we don't know how this affected Bose, for he never opened up on this matter. But one can draw one's own conclusions from the fact that for the next 16 years, he did not work on physics at all. He worked on chemistry, he worked on statistics, he worked on the ionosphere, but not on physics till 1939. Now, to come back to 1924, while Einstein was working on Bose's ideas, Bose himself carried out another investigation, leading to his second paper, And that was also refereed and published by Einstein in September 1924. And this was a brilliant paper, and it is really what we are going to talk about. And it is this paper which really established the power of Bose's counting technique, which we now know as quantum statistics. So, what did Bose do? In this paper, he extended his earlier treatment of a gas only of photons to a mixture of photons with a material gas, such as, for example, hydrogen, oxygen, nitrogen, whatever. Now, if you look at the cartoon, the blue dots represent the photons and the red dots represent the gas molecules. The whole is treated as an ideal gas. That is, no interaction between the particles except elastic collisions. The container has a very limited role to play. It holds the mixture and sometimes absorbs and emits photons so that their number keeps changing. On the other hand, the gas molecules just bounce off the walls of the container. They do nothing else. And so, in fact, know most of the photons. Now, Bose applied his counting method to this mixture with the assumption that the gas molecules are distinguishable, as Boltzmann had taken them, and the photons are indistinguishable, as he had assumed in his first paper. Curiously, what Bose reports in his paper is that in this system, the molecules follow the Maxwell-Boltzmann distribution, and the photons follow the Bose-Einstein distribution. It is therefore the counting method, the distinguishability and indistinguishability, which is needed to get the right distribution. All other factors are extraneous. So this was the final nail in the coffin of all ideas that it is the whole rock, the container, which creates quanta. No, they do not. It does not create quanta. It just confines quanta. Now, not surprisingly, Bose's conclusion upset Einstein greatly. It proved, in a sense, that the great man and all his European friends had been barking up the wrong tree. Not only was it the first time Einstein had extended somebody else's work, it was also the first time somebody was telling him to his face that he was simply wrong. And this someone was not a white-bearded, white-skinned professor from a hallowed university. No, it was a young fellow from a colonized land who came from a university that was just a year and a half old. Well, Einstein did publish the paper, but he added to it a long dissenting note in which he claims that Bose's work cannot be right for such and such reasons. But in fact, Bose's work was right, and Einstein's arguments were simply wrong or irrelevant. For example, he complains in his note on this paper that this Bose's paper does not explain spontaneous emission and absorption. Of course, it did not, simply because these were not needed for the work. I mean, to understand the stock market, you don't need to explain the nesting habits of the wild duck. Why should Bose have written about it? Anyway, but it may have been because of this dissenting note from the great man that Bose's second paper never got the credit which it so richly deserved. Instead of being hailed as a milestone which marks the real birth of quantum statistics, it remains largely forgotten to this date. Every cloud has a silver lining, so I should also say that this work was not totally wasted. The one person who read the paper and was deeply influenced by it was Erwin Schrödinger. At that time, as it happened, Schrödinger was working on the statistical mechanics of gases. And it was not surprising that a man of his caliber would immediately understand the significance of what Bose had just done. Moreover, Einstein himself, despite his grumbling about Bose's second paper, had in fact gone further himself and assumed that material gas molecules can be indistinguishable. This is what led to the Bose-Einstein statistics. Now, in that paper, he had invoked de Broglie's theory of wave-particle duality in support. He had just hinted about it, but he hadn't written in detail. But this much of a hint was quite enough for Schrödinger, and it led him to develop the wave equation of a material particle. Of course, the Schrödinger equation, which he set up, is still the most widely used equation in quantum mechanics. And Schrödinger himself went on record to say wave mechanics was born in statistics. And thus it is that we owe the quantum revolution to Bose's pioneering research, which built the launching pad from which quantum mechanics took off. Thus, when Google builds its giant computer, quantum computer, under the leadership of an Indian, you see Sundar Pichai in the picture, it is well to remember that the roots lie in the work of another Indian, Satyendranath Bose, whose picture I show you inside at the top of the machine. So, in this 100th year of quantum mechanics, it is a good time to recall the roots of this wonderful theory and give credit where it properly belongs. And thus, we should remember with utmost respect the name of Satyendranath Bose, who against all odds made such a significant and original contribution to science that we still have not seen half of the consequence. Thank you.
So that brings us to an end of our mini-series, The Forgotten Twin. We have heard three very renowned physicists express their views on Bose's second paper, Thermal Equilibrium of Electromagnetic Radiation in the Presence of Matter. All three are of the opinion that this is a very, very significant paper and deserves greater attention from the scientific community. We earnestly hope that serious students of physics will take a look at Bose's second paper, read it, understand it, and appreciate how in 1924 he applied statistical methods to arrive at some very important, significant results of matter radiation interaction in a state of equilibrium. And as viewers, if you have your own thoughts and opinions, please feel free to write in the comment box. We will be only too happy to respond to you. Thank you very much.